students. In our last lecture, we talked about Taylor series solutions of ordinary differential equation. And in this lecture, we will talk about the Picard's method of successive approximation. To understand the method, let us recall our general differential first order differential equation. This was given by dy dx is equal to function of f of xy. And we were also given this initial condition, y at x naught was equal to y naught. Now to begin this process, we will first integrate both the sides of this given differential equation from the given point x naught to any arbitrary value x, and we will integrate it with respect to x. That means we are going to integrate with respect to x dx. So if you integrate both the sides, what are we going to get? From the left hand side, obviously we are going to get, because it is derivative of y with respect to x, so once you integrate it with respect to x, we get y that and x naught to x, and if you write it properly, then it will be equal to y at x minus y at x naught, right? Now what is y at x naught? Y at x naught was given to be y naught, so we will be simply writing y naught for y at x naught, because that will be given to us. Now if I take this balloon, this minus of y naught to the right hand side, I will get this particular integral equation given in equation 7.3 here, right? And given in this. Now this integral equation will be used to find out the successive approximations, right? Now how to begin your method? So to begin with, first we will use the information that is given to us. That means we are given y at x naught is equal to y naught. So in place of this y, we will be substituting y naught, and we will carry out the calculations and find out our first approximation. Now once we obtain this first approximation, we will substitute this in this particular function, and then we will find out our second approximation. Again, with our second approximation, we are going to find out our third approximation, right? And so on. So in this way, anyone can find out the general nth approximation that is given by this formula, right? This method is pretty simple, and you might have noticed that in this, using this method, we are generating a sequence of approximations, like this is the first approximation, this is the second approximation, and so on. Now there is a condition that is known as Lipschitz condition. If your function, this given function f of xy, if this f of xy satisfies this Lipschitz condition, then this approximations y1, y2, y3, and so on, they will converge to your given solution, your required solution. Now we are not going to talk about Lipschitz condition, and we are not going to verify all this, but we are simply going to illustrate the method using an example. So let us look at an example and see whether we can understand the method or not. Now look at this particular equation. So the equation is this: y dash is equal to x plus y square. That means your f is x plus y square, right? And you're in condition that is given y equal to 1 at x equal to 0. That means, what does it mean? It means that your x naught is 0, and y naught is 1. Now using this y naught, we are going to first find out our first approximation. All right, so so let us start with this particular example. So let us find out this first approximation, y1. So see, in place of y, we have substitute the value of y naught, that is 1. So x plus 1 square will be x plus 1 dx, and x naught to x, integration was from x naught to x, and in this case our x naught is 0 to x, and y naught plus y naught was 1. So if you integrate it, you will get 1 plus x plus half of x square, right? This is our first approximation. Now using this approximation, we are going to find out our second approximation. What is that? This is the second approximation. See, x plus y square. So in place of y, now we have substituted this particular value. All right. So once you integrate, the formula remains the same. Only this successive approximations. This y1 will be used to find out y2, and y2 will be used to find out y3, and so on. So see, we can finally find out a solution. So see, these all are solutions in terms of powers of x. Therefore these solutions are falls under the type 1 solution that we already have talked about in our previous class. Now let us look at another example and illustrate the method. So look at this particular example. Now in this case, our f of xy is this is our f, and your x naught is given, it is 0, and y naught is 0. So in place of y, we will be first finding out y1. In place of y, we will substitute 0, and if you recall the method, that is y1 will be equal to y naught plus integration f of x comma y naught, right? So y naught is 0, therefore no terms involving 0 plus, so 0 plus anything is that thing. So we will be simply integrating x square by 0 square plus 1, that is x square, so x square dx. So you get first approximation. So now once you get your first approximation, you use this, that is in place of y square, see, x square by y square, in place of y square I will be using this, therefore you get this particular term here. Now once you integrate this, you get your y2, that is given by this. All right. So in this way you can use your Picard's approximation method and find out solutions of your ordinary differential equation. All right. Now I will send you an assignment where you will be asked to find out solutions using Picard's method, and in case you have any doubt, please let me know. Thank you.